So thanks for coming along. I've got a few different things planned for today, which I thought would be quite fun. So I'm Tom Hall. That Tommy Hall, you might know me as that Tarsier guy. You might know me as an elaborate scam from the internet. I want to talk about SICP Distilled, which is a project I put on Kickstarter late last year, which I described as an idiosyncratic tour of the best of structural interpretation of computer programs in Clojure. I never thought I'd actually have to say that out loud, so that was quite a mouthful. So Distilled because we're not going to necessarily do it all, and I guess tour as well. We're not necessarily going to look at it all. Idiosyncratic in terms of I might do things a little bit differently than the book, probably not wildly differently. Actually, much less distilled than I planned, because the book is so good that most of it has been carried over. So the idea is the book's already available for free. There's a nicely formatted ebook version of it, etc. And what I wanted to do was, because when I went through the book a few years ago, a lot of the things you have to kind of translate. The videos that are online of the authors talking about it use the version 1 of the textbook, and then you've got sort of incompatibilities with different versions of Scheme, and then kind of translating it into Clojure, and often kind of not having projects that easily get started, and kind of flipping through the book and finding different pieces of code, taking the code examples. So what I want, the goal for the project is have a sort of summary ebook of it, just describing the key ideas. Have projects you can download and get started straight away on. So one of those is the Escher one, which to me is like a real highlight of the first 2 chapters. So you're lucky in my opinion, the highlight of the first 2 chapters, which is where I'm up to now for the bigger project, is the Escher example, which I'm going to do for you today. The highlight of the entire book is the meta-circular evaluator. So it's the writing a Lisp interpreter in Lisp. I managed to do it in about 100 lines of Clojure on the train today. So you'll get to experience that as well. So you'll actually get what are to me the 2 main highlights of the entire book. And it was only after we had a dojo at U-Switch where I work yesterday, and somebody was doing chapter 4 of SICP, and they asked me if I'd done the interpreter, and I said, yeah, I did it in Scheme a while ago. I've done one in Ruby since, but I haven't yet done it in Clojure for the project SICP Distilled. And on the train today, I thought, well, you know what, I can probably do it now. So actually went through and did it, and so we've got something that we can take a look at and you can work on at home. After Peter Norvig says, why study SICP at all? And he says, if it's about automobiles, it would be for the person who wants to know how cars work, how they're built, how one might design a fuel-efficient, safe, reliable vehicle for the 21st century. The people who hate SICP are the ones who just want to know how to drive their car on the highway just like everyone else. So that's kind of my favourite quote about it, is you're really looking in detail at like important stuff, and people say, well, how can I use this in my day job? And so often I give talks, you know, about like evolutionary algorithms, and people say, well, how can I use this in my day job? And I'm like, well, if your day job is taking rows from a database and inserting them into rectangles on a screen, you're not going to do it, are you? Like, sorry, it's not my job to make your job interesting. So, sorry, that was a bit too sarcastic. So what the book goes out at the beginning, it says what it's not about. So it makes the point that it's not about a particular programming language, which is good because we're going to be doing it in Clojure rather than Scheme. It's not about, so they say it's not about that, but then you do along the way learn most of Scheme. They say it's not about clever or efficient algorithms, but then you do go on to do primality testing and talk about random algorithms and talk about algorithmic complexity and efficiency. It's not about the mathematical analysis of algorithms, though you do learn about sort of big O complexity and things like that. The book was the sort of intro course at MIT, so it does to an extent presume, it kind of takes the point, given that you know algebra, let's talk about this. Given that you know differentiation, let's talk about this. So in sort of distilling it, I've tried to avoid ones where it assumes differentiation and stuff like that. I've heard of people learning differentiation just to tackle SICP, but I don't think that's necessary. I think you can skip those bits and get the core message. So what it is about is it's about computation. It's about this idea that we have a new way of unambiguously expressing procedural or how-to knowledge, and we're at the early stage of it, and we don't quite know what it is, we still confuse the tool with the topic, etc. And also from an engineering standpoint, just how do we build big complicated things, and they try and get like an engineering discipline around it, which is really, really nice. The sort of line is, and I think it's originally from Dijkstra, is calling it computer science is like calling biology microscope science. It's like it's confusing the tool with the topic. So it's like calling mathematics measuring stick science or whatever. It's like we're so early in the time of this new invention stroke discovery that we don't quite know what it is. There's a wonderful talk that Jerry Sussman's done, which I don't think I do link to, but I can sort of retrospectively amend the slides so that I do link to it. But yeah, that's the key idea. Jerry Sussman has since gone and written a book called The Structure and Interpretation of Classical Mechanics, which is how to solve sort of non-quantum, non-relativistic mechanics, but expressing, again, unambiguously how to do it, because the mathematical formalism is a little bit hazy for various reasons I won't go into now. So why in Clojure? I seem to be lacking slides there. So why in Clojure? I'll show you my explanation from the actual project. So Clojure is a modern Lisp, slightly less parentheses, although that was what tripped me up today. Common statements have slightly less parentheses. More immutability, so I'll talk about this in a minute, but SICP takes you basically to chapters 1 and 2, you don't do any assignment, you're in this purely functional, nice world, and then in chapter 3 they say, oh, we're going to do something messy now, we know it's messy, but we don't have a good way of doing it. Now Haskell since come along, and Clojure has got some opinions about how one should manage mutable shared states, etc. So one of the kind of appendices to this, I gave a talk on concurrency and stuff in Clojure at the Euro Clojure, I know it was at the Clojure Exchange about 1.5 years ago, so probably an appendix will be how does Clojure handle concurrency. And yeah, targeting the JVM, it's got a nice parser library that comes with it, Instaparse, so if we were to write a parser and an interpreter for some other language other than a Lisp, we could quite easily do the parser part. So one of my extra little goals is to maybe write a subset of Python interpreter in Clojure, as well as doing the Lisp interpreter in Clojure, etc. There is a logic engine in SICP, but we've got a more featured one in Clojure land in Core Logic, and obviously different concurrency models. So, what would Rich Hickey do? Someone asked the question, is SICP a good way to learn Clojure? Rich thought no, but what I thought was quite interesting is that it's a book about programming, and then you choose a scheme because it's atomic. I won't read it, it's boring to read the whole thing, but it says Clojure is not an atomic programming language. It's too lazy and tired and old to program with atoms. It says Clojure provides production implementations of generic dispatch, associative maps, metadata, concurrency, system data structures, etc. much better than you'd get if you followed along with SICP. So what I'm going to do in the project is, where possible, use the Clojure version. So we implement sets using just lists in SICP, but from them we can just use Clojure sets if we like. We implement associative arrays in SICP, but then from them we just use Clojures. So we talk about how one might go about it with perhaps a noddy implementation, but then why not use, and you'll see in my interpreter versus the one in SICP, that just having a map structure available helps with the implementation. Why spend time doing that? Things like def type, def record makes a bunch of the sort of getters and setters that SICP keeps building for all the different things. In the Escher example, we'll see that having a built-in vector type means we can just use the Clojure vector type, and the code is much more nicer, and readable, etc. So he says, in particular, what the point I just made, which is Lisp prior to Clojure leads you towards a good path with functional programming in lists, only they leave you high and dry when it comes to a suite of data structures you need. So the problem Rich identifies with Scheme and by sort of association SICP is that you don't have the sort of rich data structures and stuff like that. I still think I think Clojure is a great language for expressing the ideas of SICP. I hope you agree after my presentation today. So the shape of the book is in 5 chapters. First chapter is fairly trivial, building abstractions with processes. This is no data structures at all, only primitive types, in fact only numbers are used, I think. So you see how far you can get with that. Chapter 2 introduces data structures. There's only one data structure, which is the const cell, and then we go and build everything from that. So this is this idea of like atomicity, or sort of very, very foundational. It's not necessarily a language that you'd want to go and build stuff in, because you'd have to go and build up a whole load of infrastructure that's already there in other languages. There's extensions to Scheme and stuff which make that less true. Racket is very, very interesting, but the scheme described in the book is deliberately very pared down. You do spend almost no time actually learning Scheme. I'll step through something I've prepared for the first chapter of the book, but I'll go through quite quickly on the assumption that you're all Clojurians already, so that we can get onto the Escher example, which is perhaps more interesting. The third chapter is that the famous one where suddenly we start mutating stuff. We can have things that variables that we change, and we have the list structure that we've got. We can change parts of the lists, so we're banging on things, and then how to manage that is the sort of thrust of that book, that chapter, and how they've avoided it deliberately because it's not a nice idea. As if you've sort of drunk the Clojure Kool-Aid, you'll know that mutable data is not a good idea. Chapter 4, so-called meta-linguistic abstraction. You're lucky today, we will be going through a Lisp interpreter in Clojure. This is the real aha moment. It's traditional to wear a fez. I'm afraid I didn't decide I was going to do the interpreter today until I was on the train, or I would have definitely bought a fez. So we get to see that an interpreter for a programming language is just a program. So that idea of things being self-hosted, etc. Chapter 5 goes through, introduces register machines. You write a compiler eventually that targets the sort of fake assemblers described in Scheme. And what typically happens is, I meant to include a link. My friend that analysed the viewing figures on YouTube of who actually sticks with the videos that the authors have. Massive drop off to the point where no one really reaches the end. So it was kind of my goal for the project as well, was get more people to the end, like stop people worrying about particular sections or whatever, and take away the sort of core lessons. So just sort of highlights. Chapter 1 and 2, Escher is already done. There's another example doing Pontoon or 21 using higher order functions, strategies of functions. You combine them using function composition. There's extended examples where you implement rational numbers and complex numbers. I'm working on something using generative testing to assert that those things are a field. So that's quite fun and introduces the idea of generative testing. Also, sort of space and time complexity is mentioned in the book. So I've got some criterion tests asserting that the fast exponential version is logarithmic and the slow one is exponential, etc. So yeah, all of that is kind of work in progress right now. The next thing after that is probably jump to chapter 4. Let's not learn about assignments in Scheme because we're not in Scheme, we're in Clojure. Jump to chapter 4 and build a toy interpreter, the sort of very beginnings of which you are going to see tonight. Then take another language, because I think it's good that everything's in Scheme, but it sometimes doesn't help, or it makes understanding harder if you're not sure whether you're talking about the S expressions that represent your language or S expressions that are Clojure, and what exactly is a val in where and things like that. It becomes a little hard. So I thought an interesting exercise might be like a subset of Python parsed using instaparse and interpreted in Clojure, because we're not accidentally cheating. I had one example on the train where I just let nils fall through, and I didn't have a nil in my language. I just let Clojure's nil leak in, and it's hard sometimes to kind of get that separation. And obviously the logic engine, going to look at, there's a book called The Reason Schema, which is excellent, and then there's core logic we can sort of crib from a little bit as well in terms of like a better description of logic. I also, as another addendum, there's a talk on parallelism by Guy Steele that I did that was part of my concurrency and parallelism in Clojure talk as well, which is written up on my blog. I'm going to also sort of do some examples of that as like an appendix as well. So we tackled chapter 3 by adding assignment to our interpreter and doing the chapter 3 exercises in our interpreter rather than having to do a scheme. So it's difficult to navigate adding things into the compiler and then doing chapter 3. There's a bit of back and forth, but I think that's the best way to do it. We introduce an idea, implement it, and then use it kind of thing concurrently rather than learn it in chapter 3 and implement it in chapter 4. Chapter 5 feels a little way off now after taking so long thus far, but my goal is to do either an actual x86 target or LLVM, so actually do it rather than compile the imaginary machine described in the scheme and simulated in chapter 5, actually sort of generates LLVM. So so today we're going to try and get to the Escher example. Hopefully you guys can work on it a bit, take a break, and then I'll talk through the interpreter. Hopefully you guys can download it and then have something to play with. So you come away at the end of today with the Escher example, which I don't know how many person hours it takes to complete. Now that you're on the GitHub org, there's a chat room in Gitter about it, and I think I only saw about 20 or 30 different people come in and talk about having done the Escher example, but it's been really fun to see people helping each other and stuff like that, so if you want to get involved in that, it'd be great. Yeah, so I'm going to come back to that in a bit, because that was another aha moment for me in SICP. I'm just becoming aware of time. Okay, so I have, who is, it's like a choose your own adventure. Who would say they were a beginner of Clojure? I don't know if that's modesty. How do I disambiguate modesty in there? Who's written a Clojure program of more than 50 lines? Okay. You're all very modest. Yeah. Okay, so you've all written a Clojure program of. Who's done Clojure cones? Who's finished or halfway on Clojure cones? Okay. I think what I'll do, because you're all so modest and consider yourselves beginners, I'll just step very, very quickly through the sort of initial thing, because it does inform our talk about the interpreter later. Or, yeah, that's what I'm going to do. So, we talk about, in both chapter 1 and chapter 2, first, what exists anyway, and then how do you build new ones. So at first we talk about primitive expressions and how to combine them and how to abstract them, and we do the same for procedures later. We say there's built-in procedures, but how do we build our own and how do we combine them? So primitive expressions, numbers evaluate themselves, and think about this. This is we hold in our heads an evaluation model for Clojure, whether you know it or not. Think of this as, I'm going to say things that are key towards how we build our interpreter later. So this is simple stuff, but how we think about it is how we build our interpreter later. So your mental model of strings evaluating to themselves, booleans evaluating to themselves, a bare variable that doesn't exist in your environment, if you evaluate that, you get an error. It doesn't exist, right? Undefined. Characters evaluate to themselves. We know how to evaluate compound expressions. The first element in any of the S expressions is the operator, or it might be a macro, or it might be a special, well, it's always an operator, let's say. An operator which is a function in the usual case, or a macro, or a special form. Special forms can have different evaluation rules. The normal evaluation rule is, and we're going to do this in our interpreter later, evaluate the operands, and evaluate the operator, in fact, as well. And then do the like a substitution, which I'll go through in a sec. So we can do multiply all those numbers together. We can say divide those numbers. And one should line things up nicely, right? So far so easy. We can name things. So once you can name things, you can refer to the name. So times A3, if A is 2, that's 6, etc. Predicates. I'm not going to go through it in detail, but the two things are equal. Clojure has really, really good equality semantics. Numbers with coercion, won't spend too long on, it's not important for today. Booleans and behave how you expect, and in fact, short circuit. And doesn't short circuit. Oh yeah, with any non, it'll return anywhere. Or behaves the way you would hope, not behaves the way you would expect. Conditionals, so we've got branching. And this is a difference from scheme. If you know scheme, there's less parens here. That's actually the error that delayed me starting. I had some notes on my blog from a while ago about the everything from nothing idea I'm going to talk about in a bit, and it was in scheme, and I quickly translated it into Clojure, just not in the REPL, just in my slide editor, and I pasted it into the REPL and something went wrong, and then it took me a little while to figure out what was going on. So that is another problem, translating things from SICP. I often leave a blank line after those because I think it groups the choices a bit better. That's not necessarily a good style, that's just something I do. So conditional, you're saying if that test is true, the answer is the thing next to it. And it does them pairwise. As I say, I add a line to make it simpler to understand. So, and then if behaves how you'd expect, if predicate then consequent, otherwise alternative, and evaluating combinations. This evaluation rule we're going to hold right as a program, because of course, program is just a way of unambiguously expressing how to do something. So evaluate, if there's a combination, evaluate the sub-expressions, that's like I said, evaluate all the operands, evaluate the operator, apply the procedure that's the value of the leftmost sub-expression, so i.e. whatever the value of the first thing in the S expression is, which we term the operator, to the arguments. I think I called them operands, sorry, that was a bit more formal than I've been in the slides, that are the values of the other sub-expressions. So we say, these are the operands, what's the value of this? And the answer is, well, it's the value of this, and it's defined recursively, right? So the value of this, the whole expression is, what's the value of this? What's the value of this? What's the value of this? Well, the value of this is, what's the value of this? What's the value of this? And we just descend, and that's how we do it. Special forms, though, do not follow that normal that evaluation rule. So def is an example of a special form, naming things. That's not the case. We don't evaluate A here, do we? Exactly, because that blows up. So special forms don't follow the evaluation rule. So far we've got primitive data, procedures, and we combine operations by nesting. We associate names with vowels. So now we can say compound procedures. So defining square, our interpreter, later does actually, this definition of square does work, which is always nice. So yeah, the first example is defining the name square to be this function. So this is like an anonymous function. The interpreter I've built only accepts this form. We do have syntactic sugaring Clojure, defn, the name of the function, the parameters, and then the body of the function. And again, these names of things are how we name them in the interpreter. So the name of the thing is square, the body is x times x, and we solve that by, I've got a slide that explains that a bit better. And then I just included here the examples in scheme, because I thought this, define square x, x times x, actually looks a bit more like the substitution model, because it's kind of saying wherever you see this, you can replace it with that. So I thought that it's a little bit more evocative, the sugared scheme version. So here we go, our model for the evaluator. Just wondering if we should do the evaluator first, now that we're here, because this feels like it's choose your own adventure, and I seem to be choosing, not you. Yeah, we're going to go and do the interpreter first, I think. So to apply a compound procedure, evaluate the body of the procedure with each formal parameter replaced by the corresponding argument. So this is the argument. The formal parameter of our function, we called it x, didn't we, I think? So the body of the procedure, we evaluated by replacing all the values of x with 5. In fact, the way we do it, this is a kind of like substitution model. So this is the first model we have in SICP of how one evaluates S expressions. In fact, we could ask, what's the value of that in an environment where x is 5? And that's actually how that's actually how the interpreter works. So just in case I'm being waffly there, the substitution model is our first model. It says take the body of the procedure and then replace, as in it's a syntactic thing. It says replace x with 5 and then evaluate. And we know how to evaluate. It's a little bit more, it's a little subtle difference. The way the interpreter will actually work is it'll say, well, evaluate that in an environment where x is 5. So as if we did def x5 before we asked for the value of this. So it's a little, something a little tiny, tiny difference. And then we evaluate it to get 25. So now might be a good time before the break, given that we've got 20 minutes, to actually go and look at the interpreter, and then we can come back and do Escher at the end. Seems that that's more, feels more apropos now somehow. So I have one small thing. Sorry to be jumping around. Another nice aha moment in SICP is there's only one data structure that they go for that's built in, and that's the const cell. And lists are in fact derived from const cells. I thought a nice aha moment, and it's not a great fuss is made about it in the book. But you have this operator const, which takes two things and joins them together. So you can name them obviously because so A is the const of 2 and 3. That's 2 and 3 joined in a pair or a const cell. If you ask for the car of it, you get 2. If you ask for the coulda of it, you get 3. And you can define B to be the const of 3 and A, so you can const things onto other things. And lists are in fact just chains of const cells with a nil terminator. So when you see a list, it's just a chain of these const cells, and this is the only data structure in Scheme. So one thing, so the car of B now is 3, the coulda of B is the pair 2, 3, so we join pairs, and it brings up the idea of closure, so as in with an S. So in mathematics, a binary relation on a set is closed if you let's say plus on the integers. If you add 2 integers, you get another element that's also in the set. So you say they're closed under addition, and it's a nice feature of this data structure that it's closed. So you can take 2 of them and join them together, and you get another one that is the same kind of thing. And the coulda of B, which is if the coulda of B is this, the coulda is the rest, if you like, and car is the first. So what I thought was quite nice is, and I just translated this just 10 minutes ago, or wherever we are, 30 minutes ago from the scheme I had. So we can actually, const, car, and coulda are the only data structures built in Scheme. And obviously you wouldn't really do this, but you can actually define them in terms of functions. So given that you've got functions, you can build the only data structure in Scheme, and you could use these as working definitions of const, car, and coulda and build everything in. And I've said it already, right? That there's only that data structure in Scheme, and everything in SICP builds from const, car, and coulda, as in like creating pairs of things, creating chains of things. Sets are done, associative arrays are done. And if you look what happens, so what it is, const of 2 things, x and y, the return value is a function of 1 argument, and all that function does is it says, well, if you give me a 0, I'll give you x. If you give me 1, I'll give you y. So we don't do any error checking here, but const, the return value of const is a function. You can define car then to be, well, that const thing, give it 0, i.e. return the first thing, yeah? Coulda is, well, give that const thing, give it a 1, and then what will it do? It will return the second thing. So you're using the idea that you close over. When you say const xy, that's in scope of this function, and it's closed over xy, so you can refer to it. Whenever you call this function now, x and y only exist inside this function, and you say, whenever I call it with 0, give me the first thing. Whenever I call it with 1, give me the second thing. And you can get const car and coulda in terms of pure functions, and it does indeed work, as you can see. I defined it before, so I can say what is the car of const 1, 2, and the answer is 1. So there's only one data structure in scheme, and we just implemented it using functions. Our interpreter that you see in a minute actually does have lambda defined, so one can, well, fn defined, so one could, you can add in scheme, in our interpreter, definitions for const car coulda without changing the interpreter, eval them in your program and build the whole of SICP. Well, I don't have booleans in the interpreter, so I'm lying. But so in terms of what needs to be built in and what you can build with just having functions is really, really nice. And the other one is an embedding of numbers in as functions called the church numeral. So one could, you can get to add by just using increment, right? And you can then do multiply, given you've got add, and the increment is just defined in terms of functions. Numbers are just repeated applications of functions that return nothing. So we can build numbers, in fact, out of functions as well. And this idea that the lambda calculus, which is what scheme or Lisp in general were based on, is a complete, in the Turing equivalent sense, way of expressing these computational ideas. So I thought that was quite nice. I'm now going to spend perhaps 5 or 10 minutes, because we agreed to break at 8 o'clock for pizza and stuff. So has anyone got any questions about what I've said thus far? Was it all too easy, or? Okay. So we'll look at the interpreter. So. Is anyone else really depressed by that font, or is it just me? No, okay, let's do this. Just looks normal. Or you don't know what I should have. I do know how to split Emacs windows, I promise. Oh my word, I'm too tired. It's like pushing and pulling the door and getting it wrong 3 times, isn't it? Okay, there we are. Whew. So go into the mini Lisp namespace. So I should show you the tests as well. So one thing that you need to understand before we have a look at the interpreter, actually I didn't mention it here, sorry. I've given you what is like an entire semester's worth of stuff sort of squished up into an hour, so I hope it whets your appetite, and I hope my lack of clarity doesn't put you off. The core idea is you have 2 functions, eval and apply, which is exactly like our substitution model. We said, what is the value of this, what is the value of this? Oh, it's a function application. Well, then I need to evaluate the argument and then evaluate the operand and then do the substitution. So I'll just step through it now. So in terms of tests, I've said, is 3 the value of, I've called it, there's already eval in Clojure, so I've called it eval sexp, so eval S expression. So the S expression 3, which is a valid S expression, in the environment where nothing is set, and is the value of it free, so this is a sort of bare bones thing. Test variables, so can I look up the value of A in an environment where A is 2? And again, to ease implementation, I've used Clojure's maps as the environment here. In SICP, you have a lot of like lookup functions and extend environment type functions. Obviously, we've got an associative data structure anyway, why not use it? So, can I define things? So if I say, and I've had to quote here, right? So this is the subtlety. If I just do def here, then def A3 gets evaluated in Clojure. But if I quote it, I'm saying treat that as data and pass it into the eval s expression thing, and then, oh, I've been naughty, I've asked for the second one of them. Yeah, because I know that it returns a pair, the second thing is the environment. So I'm saying if I eval def A3 in the empty environment, does it add something to the environment, right? So it probably makes sense to look at the actual interpreter now. So the whole thing is 109 lines, but I actually leave the extra space in between the cons. So I like to say that was 100 lines. So our evaluator, which is where we start, and it's evaluating S expression. This isn't what is done in the book. This is an idea I took from somewhere else. In my brain, I'm remembering that it's a monad, so it might be from a Haskell Lisp building tutorial. But instead of returning one value, I actually return a pair. So I always return from eval sexp a pair of the value on the left and the environment on the right. So some of the things we do change the environment. Some of the things we do some of the things we do have a value. So a program is a sequence of S expressions, and we just look at the return value of the last expression, a bit like do does in Clojure, right? You say do, and then a sequence of expressions. The value of the last one is what counts as the value of the whole expression. So we say if it's self-evaluating, so we just ask it's a conditional. We say if that thing's self-evaluating, then the value of it is itself, and the environment is unchanged. I think that's clear, right? If you ask for the value of something that's self-evaluating, like a number, it's just that, and we haven't changed the environment. If it's a variable, then look up in the environment. Remember, the environment is a Ruby. It was once a Ruby. The environment is a Clojure map, so we can just use maps as functions, which is a neat trick of Clojure, right? The fact that keywords are functions of maps, and maps are functions of the keywords, of the keys, etc. So we look up in the environment what the expression is, because it's a variable, and we don't change the environment. If it's a definition, then we return nil, which is an implementation detail. It's undefined in the scheme spec, actually, what the return value of an assignment is. But then we have to change the environment. So we say the name is, and I've got an accessor function here called defName. This is more in the SICP style. So I'll refactor this probably to be better Clojure at some point. But we say, well, we want the name part of the S expression, which is using this defName function, all of which exists in the same file, which we can look side by side in a minute, but I just want to go through broad strokes what's going on. And then we look up the value, so we look up the name bit of the S expression, we look up the value of the S expression, and we know it's a def expression because this conditional is true, so we're saying def something is some S expression, right, at some point in our program. And we say return value is nil, but we do need to change the environment. So we say associate in the environment the name with the value of S expression. So we're recursing in, we're saying some S expression here is the value of this name. So we said def A is some S expression. Well, we don't want that S expression, we want the value of it. So we say evaluate S expression, that value in the current environment, and add it into the environment. Does that make sense? So what's the value of that S expression in the current environment, add it to the environment with that name, so our definitions change the environment as they should. I hope that's clear. If the S expression is a function, then we make a procedure. This is the subtle part, but we're almost finished now, right? We're almost finished. If it's a function, i.e. it says the first element of the S expression is fn, exactly like Clojure. So while this looks like Clojure in this respect, then the value of it is this make procedure, which is something in our language. Sorry, which is something in Clojure that represents the concept in our language. I'll jump to the definition of make procedure now. We want the parameters of the S expression, i.e. fetch out, if it is a function of x and y, fetch that out, the second element, right? So maybe concretely if I look up here. What we're parsing now is something that looks like this. Can you see on the left, line 23? Function of xy is plus xy, for instance. So concretely, we're parsing something like this. We're saying, is it a function? Well, yeah. And then I want this part, which is the, where are we? Yes, sorry. It's the function params of the S expression. So i.e. this bit, the parameters, the formal parameters, x and y, and the function body of the S expression, which is this bit. And then we're going to, because remember in Lisp, the function, when it's defined, closes over variables in the bounding scope. So you need to know what the environment is then. So at the point this function is defined, we look at the parameters, look at the body, and look at the current environment. So I'll show you what that function looks like. So it looks like what's it called, make procedure. And this is where I'm halfway in, oh no, not in the test, in the actual file itself. I'm kind of halfway in between the Clojure style and the SICP style. So make procedure takes a params, a body, and an environment. What SICP does then is builds it out of const cells, but we've got a richer data structure, haven't we? So we're going to hold these three things, params, body, and env. We'll store it as a hash, as a map. Sorry. So our procedure, when it's exec in our interpreter, so it takes a value that says function of x and y to some S expression. We actually capture the params, capture the body, and the current environment gets captured as well. And at some point, we're going to apply that procedure, right? Which is what this next thing does, which is the only other thing now, the kind of catch-all is, well, if it's not a definition, if it's not an actual function, anonymous function definition, then it is, therefore, an application. In which case, the value is, I'm going to apply, which is a second of our mutually recursive functions. If it's an application, then I'm going to apply the procedure. And again, it's calling itself recursively as well as calling the other function. It says, well, what's the value of evaluating the operand, we said, yeah, of the S expression in the current environment. So that's the thing we're calling that gets passed to apply. And this is, again, taking advantage of the fact that we're in Clojure. If you do SICP, you build a map function, but then they don't necessarily use it later. And so we've said map across all of our operands, fetch the values. So we pass in, we don't change the environment. The value of it though is applying the procedure. And this is what we did for the first thing, was look at the leftmost value of the S expression, and that is our procedure. And it's the value of evaluating the S expression on the operator. Operator is just the first thing in the list. Operands is the rest of the list. We could have just written rest here, in fact, in Clojure. Yeah, so we've gone through. We've evaluated all of the operands, and we've mapped this eval itself. So we'd be in trouble with implementation here because these are not necessarily tail recursive, are they, in Clojure? So it might be some issues, but we do recursively call S expression on the operand, and then we map evaluation across all of the operands as well. Does that make sense? Somewhat? Might it make more sense if you look at it? I'm realising Peter's about to arrive, and we're about where I said I wanted to be. And then, if that doesn't work, there's no reason that should work. That shouldn't work, because we've captured all the cases that we currently need. But then I've just put it to echo to the screen eval fail. If we ever see this, we know we've dropped through and we shouldn't have. We should have captured every possibility at that point. So for each of these things, we can go through and just take a look at what it was. So when we're asking, is it an application, right? Application, S expression, and every one of these little functions, application just says, well, is it a sequence? Yeah. That's after it's already failed to be a definition of variable or self-evaluating. So self-evaluating, is the next expression self-evaluating? Well, what things in my Lisp are self-evaluating at the minute? Just numbers are, and just primitive procedures are. So every single one of these, is it a function? Can you see where I'm highlighting? So is that a function? And function question mark just looks like that, and it says it's a sequence, and the first thing in it is the two character variable fn, right? So we just ask of each thing, is it a function, is it a def? In which case we do these special things. Otherwise, as an application, the first thing in it therefore must be an operand. The rest of the things are the operators, and they need evaluating recursively as well. So if I go through for 2-3 minutes the apply function, which is shorter, which I've called apply proc because Clojure has an apply function. So this is the function that applies a procedure. It says, well, if it's a primitive procedure, then just call the apply primitive function on the procedure with the args. If it's a compound procedure, i.e. any other case, then just find the value of evaluating the S expression of the body in the environment where, do you remember like I said with this substitution model, if it's a compound procedure, we want to find the value of evaluating the S expression, which is the body. So evaluate the body in the environment where, so take the environment stored, the closure of the function, extend it with